This is lecture 9, so we're switching gears from our study of rotational dynamics and rigid bodies to a new topic. This is chapter 15 of the book. Our new topic is oscillations. So first let me give you an overview of what we'll do in this chapter. So we'll learn about systems that oscillate. In particular, we'll focus on the simple harmonic motion, which we'll define shortly. So what are oscillations? Well, it's a motion or dynamics that's repetitive. So it goes back and forth around some equilibrium position. And there are several kind of key quantities that we use to talk about oscillatory motion and talk about oscillation. So these quantities are the amplitude, how big like the maximum displacement is, how far you move away from your equilibrium position as you go back and forth around it, the period, the time it takes for the motion to repeat itself, for you to come back to the place you started with, and be at the same position with the same velocity, so everything repeats itself, and the frequency, which is simply defined as 1 over the frequency, or the number of oscillations, the number of total back and forths or cycles that you get in unit time. So the simple harmonic motion is by far the most important type of oscillatory motion. We will see why it's so. It's kind of the solution to the simplest equations that govern the dynamics of oscillatory systems. And the main property of a simple harmonic motion is that the dependence of, let's say, the quantity that oscillates. So for example, this is a distance on time is a sinusoidal function. So a sine or a cosine of something that's linear in time. Okay, so let's keep going with this. So there are a few systems, kind of canonical examples of oscillatory dynamics, which we'll talk about. So one is a mass connected to a spring, the other is a pendulum. But any system that has a linear restoring force undergoes simple harmonic motion. And this is much more ubiquitous than you might think, because any system that has a stable equilibrium, as long as your distances are small, you just perturb it a very small amount from that equilibrium position, a linear restoring force is a good approximation. So that makes simple harmonic motion a very general thing that happens for small oscillations around equilibrium. A very useful visual picture to think about simple harmonic motion is to think about circular motion with constant angular velocity, and look at the projection of this particle that's moving around the circle on one axis. So it turns out that mathematically that projection behaves like the cosine of an angle that has a linear dependence on time, and this picture allows us to solve problems involving harmonic oscillators relatively easily. There are energy considerations, like in any physical system, in systems that undergo oscillations. So there's just there's a back and forth between kinetic energy and potential energy. So in a system that undergoes simple harmonic motion, the total energy is conserved if there's no friction, and the energy keeps kind of going back and forth between potential and kinetic. So the kinetic, let's say that's the kinetic, keeps going up, and at the same time the potential goes down until the kinetic reaches its maximum and the potential reaches its minimum, and then things reverse. The potential goes up, the kinetic goes down, and this just keeps repeating itself. There are damped oscillations when there is a friction, where you have this up and down, you have this back and forth motion around the equilibrium, but the amplitude decays in time, so there's going to be an envelope for this entire time-dependent position. So that's a broad overview of what's coming in this chapter. So we'll start our discussion by talking about the kinematics of simple harmonic motion. And of course, why it's important, well, as I said, it's ubiquitous in many different systems. So in mechanical systems, electrical systems, chemical reactions can exhibit this type of back and forth phenomenon, atomic systems. And yeah, and it's helpful to know this, right? To know the response away from equilibrium if you're trying to design a system, for example, that's supposed to be in equilibrium. And then, as we'll see in the following chapters, understanding oscillations really provides a foundation for understanding wave phenomena. So it's a very foundational problem in physics and in science more broadly. Okay. All right. So as we said, oscillatory dynamics is defined as something that changes as a function of time in a periodic way. So let's go to the notes. Definition is any quantity, so it can be a distance, it can be the position of a particle, it can be, for example, an electric current in a circuit, any physical, measurable, observable quantity that has a periodic dependence on time oscillates by definition. So as an example, take a mass on a spring, simplest, most widely used example here. So you have a mass on a spring, let's say that's the natural length of the spring, and then you pull this, so the spring gets stretched, and let it go. Well, what's going to happen is now the spring is stretched, so it's going to pull it back, so it moves this way, and when it reaches the natural length of the spring, there's no force, but it's acquired some velocity this way, so it will keep going and it will compress the spring. So then the spring will apply force to the right, slow it down, and ultimately it comes to rest somewhere on the other side. So now the spring is really compressed, and now it's lost all its velocity, and the spring is now pushing it back. So again, it keeps going this way, comes back to this original position when we had stretched the spring. So let's say that's natural, and this is initial pulled spring. So if you think about the position of this, let's say then this is x0. So we put the origin of our coordinate system at the natural equilibrium position. Then when initially it's stretched, well, if I think of x of t as a function of time, and this is time, it's going to be somewhere here. It's how much I've stretched it, and then it gets closer to 0, right? It's coming back, it's being pulled toward the origin, and then it keeps going, and then turns around when it reaches here, when the spring is fully compressed, comes back, goes up, and see, once you reach this point, everything that follows is basically the same as when you started. So it goes up, goes down again, goes up again, etc. So if I call this distance here, the distance between two maxima, if I call it t, this function, I call it capital T. This function x of t has the property that x of t is x of t plus capital T, right? So if I take any point, let's say I take some point here, and add capital T to it, it's going to go here. And then you will see that, so if that's, again, t, this height here is x of t, this height here is x of t plus capital T, and they're the same thing. So the motion just repeats itself. So if you just focus on one period, let's say you know the dependence of position on time, between 0 and capital T, it has some shape, then you just keep like copy pasting that shape in front of it, and you know that the motion for all later times. So any periodic time dependence that goes back and forth is called an oscillatory motion. So these are a couple of examples here. So see that one, the first one, the one on the top has some linear motion, you know, something goes up linearly, comes down linearly, goes up linearly, but when it reaches, let's say, from this peak to peak, from maximum to maximum, then what follows is exactly what happened after this. So it keeps repeating itself. So this is a more general oscillatory motion. Simple harmonic motion, which we're most interested in, has sinusoidal dependence on time. So this is, for example, a sine function of something that depends on time. So this capital T is known as the period of the motion. Let's go back here. So this is known as the period of motion. And we also define frequency f1 over t, which is physically the number of cycles in unit time. Right, so capital T is the period for one full cycle, right? So let's draw a bigger figure, for example, here with showing lots of periods. So that's 1t here. Then the thing repeats itself. Again, that's 2t here. Repeats itself. That's 3t here. Okay. Now, if I'm interested in how many cycles I have in 1 second, notice that if, for example, here this time is 1 second, I have 3 cycles per second. So that implies that t is 1/3 of a second. So the way the frequency is defined, it has units of 1 over time, 1 over second or hertz. So units of frequency. F is 1 over s, or also known as hertz. But it's clear that F times t, right, the number of oscillations per unit time, so a number that has unit 1 over s times time that has units of second, is a dimensionless 1. So this gives an interpretation to our definition of frequency as 1 over t. Okay, so we have these two quantities, right? One is the period, again, how long it takes for the x of t to repeat itself. And then f we defined as frequency, and we define it as a dimension full number, right? It's not just a number, it's the number per unit time, so we give it units of 1 over second. And then the number of oscillations times the time of each must be 1. All right, so then the next thing is how big these oscillations are, right? How far away from the origin or from the equilibrium position you move. So let's say this is A, this is minus A. And A, which if we're talking about distances, has units of meters, but it really depends on what we're talking about, right? If you're talking about electric currents, A has units of amps, for example. A is known as the amplitude. Okay. So if I want to write an equation that describes this, so let's say I started from, let's say we start from the maximum, right? I do something like this. So let's say that's x of t. This is t. The period from maximum to maximum is capital T. And I want to have a sinusoidal dependence on time. So this motion, we can write it as x of t is a. So let's say this is a. Here we have minus a. We can write it as a times cosine 2 pi over capital T times small t. Okay, so let's try to make sense of this. Well, a cosine, right, is between -1 and 1. So if you have a unit circle, if that angle is theta, the projection, this is cosine theta. So cosine of 0 is 1, cosine of pi is -1, cosine of 2 pi again is 1. It keeps repeating itself. And of course we have cosine of theta plus 2 pi is cosine of theta. Right? So if you add a 2 pi to the argument of cosine, you're going to get the same thing. And it's something that oscillates in a sinusoidal manner between -1 and 1. So if you take a cosine and multiply it by a, well, it's going to oscillate between -a and a. So that's fine. And then, see, when we add a time capital T to our time, we should be adding a 2 pi to the argument of the cosine, right? That's a statement that the period of this motion is capital T. So x of t plus t, because we chose this coefficient with some foresight, this becomes cosine of 2 pi over t, t plus t, and that's a cosine 2 pi over t, t plus 2 pi, which is a cosine 2 pi over t times t. So that's kind of the general structure. That's how the period appears in a sinusoidal time dependence where the period is capital T. That simply follows from the fact that the period of cosine theta is 2 pi, right? So you have to add a 2 pi to that phase to come back to your original position. So for this one, where I started from the maximum, we wrote cosine. You can see for this one, where you start from 0, this can be written as a sine 2 pi over t times t. Right? The difference is it starts from 0. So harmonic kinematics is characterized by an x of t to being a times cosine omega times t plus some phase, phi naught. And omega is just 2 pi over t, where t is the period. So phi naught basically tells us the initial condition, like where we start from. Something like this, let's say you have the cosine, but let's say your origin of time is not here, it's somewhere there, right? So let's say that's the origin. So if I erase this line here, well, you can describe this in general by this type of expression here. Omega also has a name, is known the angular frequency. Is known as the angular frequency. So we have a couple of relationships between these quantities that we define. We define the period, and we define the frequency, and we define the angular frequency. So let's write these. So we wrote f is 1 over t. Omega is 2 pi over t. And that gives us a relationship between omega and f, right? Omega is 2 pi times f. They're basically the same thing related by a factor of 2 pi. All right. Now, the next topic is, well, so far we talked about how the displacement in a simple harmonic oscillator, if we're talking about a mechanical system, so let's say x is really the distance or the position of a particle that undergoes oscillations. So think about this particle attached to a spring. So we talked about how the position depends on time in a simple harmonic motion. So we had x of t being a, the amplitude, the maximum displacement, times cosine omega t plus some phase, which describes the initial condition. When do we set the clock? What time we call our time 0, basically. Now, as usual, we can talk about velocity and acceleration, right, in a mechanical system, right? So those are the kinematic relationships. So if I have this general form for my displacement, again, let's consider this example here. So say that's the natural length of the spring. So this is x equals 0. And then you measure your displacement from this. And then you have this object that kind of goes back and forth between or around the equilibrium position. And then this maximum displacement from the equilibrium is a. On the other side, it goes to minus a. And it's going back and forth like that. So you're gonna like look at it at some initial point. So I'm gonna draw something arbitrary. It's neither a sine nor a cosine. I'm gonna draw it with some phase shift. So for example, a sine would start here. So let's say it's doing something like that. Between a and minus a. So this is again time. This is x of time. Right, so I'm thinking about some general motion like this, and I know, let's say, the dependence of my displacement on time, and omega, as we said, is 2 pi over the period. The period is the distance from peak to peak. That's t. Or from minimum to minimum. That again works. Distance from 0 to 0 doesn't work, right? That's half the period. So why is this? Like, it comes back to the original position, but when it's here, it's going down. When it's here, it's going up, right? So that's not repeating, right? So to repeat the motion, you need to have both the same position and the same velocity. So this 0 is the same as this 0, but this 0 and this 0, one of them has a negative velocity, one of them has a positive velocity. The velocity at the maxima and minima are 0, right? That's the turning point. So you reach the maximum, that's when you turn around. So you've reached 0 velocity. And the direction of your velocity changes, the velocity kind of switches sign. So if I now think about velocity as a function of time, well, what would I see? First, let's do it algebraically. I know it's going to be the derivative of x of t with respect to time, right? So v of t is d dt of x of t, which is the time derivative of a cosine omega t plus some constant. So the only time dependence is in t here. The derivative of a cosine is minus sine, right? And I have to take the derivative of the argument. So it becomes minus a omega sine omega t plus phi naught. Okay. So if, let's say we look at a couple of cases. So here, for example, at the maximum, the velocity is 0. So we identify that point. Let me see if I can draw a good figure here. Yeah. Then you have some negative velocity, right? And when the position reaches 0, it seems your velocity becomes the largest possible negative value it's going to take. So it's going to be somewhere here. And then again, it reaches 0 at this point. So it's going to, and then again, it's going to reach 0 at the next maximum. So it means it's going to go up and come down. The next minimum, it's going to be 0 again. So something like this. Here it's up a little bit, maybe that way. Right, and it continues in the same way. So again, at the next maximum, the velocity goes up and comes down and reaches 0 again. So that's both like a geometric way of thinking about the velocity and the the algebraic in terms of the expression. So as a simple example, let's say phi naught is 0. So x of t will be a cosine, so that's the maximum. And then this is a. So now its velocity should be, the expression tells us that it's minus sign. So the sign would start from 0 and go up, and minus sign would start from 0 and go down. And that's exactly what we'll see here. So this goes between a and minus a. The velocity goes between omega a and minus omega a here. So one lesson is that the maximum velocity or the maximum speed that you can have is omega a, right? That's a useful expression. We can similarly think about the acceleration here. So let me write these equations again. So we said x of t is a cosine omega t plus phi naught. We said v of t, the velocity is minus a omega sine omega t plus phi naught. And if I take another derivative, I can say what the acceleration is as a function of time. So that's going to be minus a omega squared. The derivative of sine is now cosine. The derivative of omega t plus phi naught is just omega. So that becomes cosine omega t plus phi naught. And interestingly, you see that this is just proportional to the displacement. So that's minus omega squared times x of t. Okay, so these are the key equations for the kinematics of a simple harmonic oscillator. Let's take a look at a problem here. So get a piece of paper, pause the video, try and find the solution to this. All right. So what does it say? So we have a glider attached to a spring. We pull it 20 centimeters to the right, release it at t equals 0. It makes 15 oscillations in 10 seconds. Part A, what is the period of oscillations? So if in 10 seconds I make, or it makes, the glider makes 15 oscillations, what is the time of one oscillation? So I have to divide 10 by 15, right? And that's the period. What is the object's maximum speed? All right, so let's go back to the notes. So this is example 15.1 from the book. So A is just a period, so we say in 10 seconds we make 15 oscillations. What is the time of one oscillation? So that's going to be 10 seconds divided by 15, and it's whatever it is, right? It's 10 over 15 seconds. B is saying what is the maximum speed? Okay, so let's read it together again. It says initially we pull it away from equilibrium by 20 centimeters. So that's our maximum displacement, right? Then 0.2 meters is our A, is the maximum displacement, and we want the maximum speed. So we just found that the maximum speed is A omega A is 0.2 meters. Omega is So this is t, right, the period. Omega is 2 pi over t. So that's going to be 2 pi over 10 over 15. So it's going to be 15 times 2 pi over 10. So 15 times 2 is 30, divided by 10 is 3. So that's 3 pi. The units are rad per second. So therefore, my Vmax, and of course, radians, that's not a real unit, right? It's a way to think about angles. So 1 over second is also acceptable. I mean, 2 pi, we can think of it as a dimensionless number. Then the velocity is 0.2 times 3 pi meters per second. So that's 6 over 10, which is 3 pi over 5, for example, meter per second. It's the maximum velocity. And finally, what's the last part of the problem? It's saying what are the position and velocity at t equal 0.8 seconds. So now we have to use our equations, right? So first, we know that at t equals 0, it's at the maximum to the right. So what's going to happen is it will look like this. So at t equals 0, our displacement is the maximum, and it's to the right, so then it will move to the left, right? It comes down, it comes closer to the equilibrium. So this is just a simple cosine. So phi naught is 0 from this. So we can write x of t is just a cosine omega t, and v of t, as we found, is minus a omega sine omega t. Again, it's just phi naught set equal to 0 in our general equation. So we have t, we have a, we have omega, so we just plug them in. So x of, I guess, 0.8 becomes, for a we had 0.2 meters. We want cosine of 3 pi times 0.8. And then we just plug in the numbers. That's going to be in meters. For the velocity, we have minus 0.2. Our omega was 3 pi. 3 pi times sine of the same phase. And that's in meters per second. So that's a good exercise. Relatively simple. We're just given some description of what the motion looks like. We're given kind of the period in words. And we calculated the maximum velocity, and then we calculated the velocity and position at some given time, at some later time, by just using the kinematic equations of simple harmonic motion. So yeah, so our frequency is 1.5 is 15 oscillations per 10 seconds. Our period is 1 over that, which is 10 over 15. So numerically, that's 0.67. We had the maximum velocity. So we found it to be we found it to be 3 pi over 5, right? And the numerical answer is 1.88. That seems to work, right? 3 times pi is 9 point something divided by 5, slightly less than 2. And then finally, we can write the position and velocity and just insert the time, so we get some numbers. All right, so the next thing that we already a little bit discussed this, but it helps to make it more explicit. There is this mapping, as I mentioned, between simple harmonic motion and rotational motion with constant angular velocity. Right, so one way to think about this is to think about a point particle or a ball that's on a turntable is undergoing rotational motion with constant angular velocity. So this is rotating counterclockwise this way. And then you look at the projection of this motion on the plane, right? So you have light from a projector, and then you see where the shadow is. So it's going to be, as it rotates, it comes to the center, it moves this way, moves back. So it's going to move back and forth around the projection of the center of the turntable. And this is the same as a simple harmonic motion, right? Because the angle for a particle that's rotating with constant angular velocity is omega t plus the initial value of the angle, right? And then the projection is just the cosine of that angle. Now, if the radius of this turntable is a, is the amplitude, then mathematically that x coordinate is precisely the equation we had. So let's just make it more explicit here. So, sorry. So relationship between simple harmonic motion and rotation. So consider this circle here. Let's say you have a circle of radius a, and you consider a particle that at time equals 0 is at some angle phi naught at t equals 0, and then rotates with constant angular velocity. So then, let's say a later time is somewhere here, this angle phi becomes phi naught, the initial one, plus omega times t, right? That's the rate of change of the angle. And if a time t has passed, the angle has increased by omega t. Now, from here to here, we have a. So this projection, so let me draw this again. From here to here is just a cosine, right? This is phi, is a cosine phi, which is a cosine omega t plus phi naught. So that's very helpful in visualizing simple harmonic motion, right? We think about rotation with constant angular velocity, and basically now this omega and the omega we defined in the oscillatory motion are the same thing. One of them we called angular frequency, the other we called angular velocity, but they're basically the same thing. They just have different names in different contexts, and they map to each other. All right, so let's keep going with this. So that's a cleaner picture. It's basically the same thing I drew, so so now let's go through a few examples. One terminology that's useful, this phi naught is called the phase constant. That's its name. All right, so these are a few examples of different phase constants. So this phi naught we just said, it tells you like what is the initial condition, right? Where do we start? So these are a couple of examples. Let's say one has phi naught equal pi equal 3. Okay, so pi equal 3 is here. From here to here is 60 degrees. So that means at time equals 0, the rotation we mapped our oscillation to has an angle pi over 3. So it starts from here and then it keeps rotating with constant angular velocity. So what is the initial value of position? Well, the cosine of pi over 3 is 1/2. So the initial position will be at a over 2. So if I now plot x of t, which is this projection, right? It's from here to here. That's a over 2 at t equals 0. And then as it rotates, this particle is getting closer to the y-axis. So it means x is going down. It's getting closer to 0. Then it keeps going. It goes up, etc. So the phase constant really tells us how things start. If you think about the velocity at this point is negative, right? It's moving to the left, right? The projection is moving to the left. X is getting smaller. And that also ties in with the derivative of this curve being negative. So it starts from some negative value. And then the turning point is here. So when the cosine becomes 0, that's where the sine has its maximum value, right? Remember, sine squared plus cosine squared is 1. So when the cosine becomes 0, when the actual displacement becomes 0, that's when you have the highest speed. So you see this minimum here corresponds to that turning point, and you keep going, and then the green line is just a derivative of this. Again, here when the position is 0, you have the maximum. When the displacement has a minimum or a maximum, the velocity or the derivative is 0. Tangent to this curve is 0. This is a different case. The phase constant is minus pi over 3. So see, we start right at the same position. We start at x of 0 being equal to a over 2, because cosine of minus pi over 3 is also 1/2. However, here when our phase constant is negative, we have this convention of always going counterclockwise. So we see that the displacement increases. It's moving toward the maximum. It's going up from this point. And then it has a positive velocity. So yeah, so knowing that phase constant not only determines the initial value of position, it also determines the initial value of velocity, and knowing these two will give us everything that follows, all the positions and velocities that follow. This is another example, phase constant equal pi. So now at pi, cosine of pi is -1, so we start from minus a. Again, going counterclockwise, we have to go up and get closer to the center. The velocity is positive. Okay. So this is another example. Let's think a little bit about this. So we have an object on a spring that oscillates with a given period. the amplitude is given. At time equals 0, it's 5 centimeters to the left of equilibrium and moves to the left. Okay? And then we want its position and direction at a later time. So this is a good place to stop for this lecture. I leave this problem as an exercise, so you'll have all the time between this lecture and the next lecture to try and work it out using this mapping that we just discussed, right? So knowing the initial position and knowing the direction of the initial velocity, we should be able to extract phi naught and then plug it into the general equations and find the position and the direction of motion at some later time. So yeah, so we'll start the next lecture with this problem, and hopefully you will have solved it by then.